Hello, I'm Bob, and this is the Home Bitcoin Immersion Mining channel. In this design series episode, I'm going to cover how to size a heat exchanger. But before getting into the video, I want to mention some sponsors of the channel, the first being Brains. Now, I've been using Brains products and services for a while now, and one thing I think is really cool is how the different parts of the Brains ecosystem work together. First, the Brains OS sits on your miner, optimizing your miner output. The Brains Toolbox can then be used to monitor and manage all of your miners remotely. And the Brains Mining Pool and the Brains app can then be used to monitor the performance and payout of your entire mining farm. All of this works together out of the box. There's no code to write, and setup and configuration is super easy. I think it's really cool to have a complete mining solution from a single source that pretty much does it all. Next up is SAS mining. Now, the focus of this channel is home mining, but let's face it, home mining isn't for everyone. Maybe your power costs are too high, maybe you live in an apartment, or maybe you just don't have enough time or expertise to build a home setup. In any of those cases, SAS mining is for you. SAS mining offers Bitcoin mining as a service. You pay for the miners and a monthly service fee, which includes electricity costs, and SAS mining takes care of the rest. In return, you get a monthly Bitcoin payout from your miners, which allows you to build your Bitcoin stack at a discount. And if you act now and click the affiliate link below, you can get a $50 discount on every miner you buy. If you're looking for hassle-free Bitcoin mining, SAS mining is a fantastic option. And last up is the mining hardware supplier for the channel, Altair Bitcoin Mining Solutions. Altair is your one-stop shop for any mining hardware you might need. They have everything from the latest and greatest miners to every hashboard, cable, and part you might need to repair your existing hardware or build your own 120-volt home-built miner. Altair has years of experience working in the Bitcoin mining industry, running their own mining farm, and they've worked with all different scales of mining operations. Altair is based in the US and has top-rated customer support. And so if you have any question about anything at any time, they are there to help you out. Altair is a huge supporter of the home mining community, so if you're looking to buy your next miner or miner parts for your home setup, check out their website at the link below. You'll find pretty much everything you'll ever need. Okay, so when you're building your own home Bitcoin immersion mining system and using that miner to heat your water or heat your house, somewhere along the way, you'll have to transmit that heat from one fluid to another. And the device best suited to get this done is a brazed plate heat exchanger. Now, I've talked about these in past episodes where I've used brazed plate heat exchangers in my home design. I've got a link below if you want to catch up on that content later. But in those episodes, I always kind of sidestepped how I chose the size of my heat exchangers. I did this because sizing a heat exchanger is kind of tricky and it was just too much content to fit in. So I figured focusing a single episode on heat exchanger sizing might be useful, and so now I'm going to do my best to show you how I get this done. Now, the first step is to take a step back and realize that a heat exchanger just moves heat from one fluid to another. Energy can't be created or destroyed, and so the amount of heat given off by the hot fluid is going to be the same as the amount of heat absorbed by the cold fluid. And this is where we have to get into a little math. On both sides of the heat exchanger, there is a fluid flow rate and temperature change of the fluid passing through that side of the heat exchanger. Each fluid has its own specific heat and density, which together measure how much heat each fluid can hold. And when you put all of this together and get the units right, you get an equation that can help you get some important inputs for that heat exchanger design. For example, let's say I have a miner tank with two full-size miners. Let's say I want to do some overclocking and run them so they generate about 8 kilowatts of heat. At this power level, I need about 6.3 gallons per minute of dielectric fluid flowing through the tank and heat exchanger to keep them cool. And to protect my miners from overheating, I'll set the maximum output temperature of the tank, which is the input temperature of the heat exchanger, to 130 degrees Fahrenheit. If I'm using a typical dielectric fluid, the math shows the output temperature of the fluid exiting the heat exchanger and re-entering the tank will be about 110 degrees Fahrenheit. Looking at the other side of the heat exchanger, maybe I've got a 50-50 mix of propylene glycol and water providing my cooling. Now, since the dielectric fluid is giving off 8 kilowatts of heat into the heat exchanger, the glycol water is going to have to absorb that same 8 kilowatts of heat. Now, let's say I have a dry cooler outside dissipating this heat to the open air, and it's the middle of summer on a really hot day. Maybe the fluid coming out of the heat exchanger is 115 degrees Fahrenheit, and maybe I've got a pump moving 6.9 gallons per minute through the cooling loop. Doing the math, this gives me a fluid temperature of around 108 degrees Fahrenheit going into the heat exchanger. Now, with this framework in place, you can play with the numbers to see how changing temperatures and flow rates affect the different input and output temperatures. But all of this assumes the heat exchanger is perfect, and it's not. Real heat exchangers have limits on how much fluid can flow through them and how much heat can be moved from one fluid to another. And this is where heat exchanger manufacturers come into play. They know how their brazed plate heat exchangers work and have done a ton of analysis, measurements, and modeling to really understand the performance of their hardware. With your guesses at input and output values, you can call them up and work with them to figure out the real final flow rates and temperatures, and then figure out which specific heat exchanger model will work best for your setup. If you're building an industrial size system, this is the right path. You really should get their help. But if you're working on a home setup, or maybe you just want to double check what the heat exchanger manufacturer is telling you, there is one tool I found that can really help you figure this out for yourself. The SWEP company is a worldwide producer of many different types and sizes of brazed plate heat exchangers. And they have developed the SWEP software package, or SSP, that can be used to figure out which heat exchanger will work in your setup. There are online and standalone versions of this application, and both are completely free. The one downside is the SSP software will only select SWEP heat exchanger models. If you want to use models from other manufacturers, you have to make some guesses about the equivalency between the SWEP models and the models made by others. Now, this software is fairly powerful, so I'm just going to focus on setting this up and running this for a simple heat exchanger, moving heat from a dielectric fluid to a 50-50 glycol water mix. Now, I'm using the standalone app, but the online app should work the same. After downloading and installing, this is what you'll see. And the first step is to set up the software with the right fluid property data. Now, the SSP software comes with a fairly expansive library of many industrial fluids, but dielectric ASIC cooling oil isn't one of them. I looked through the SSP library, and there is a listing for something called Transcal LT, which has properties fairly close to dielectric fluid. If you don't have the detailed data for your dielectric fluid, you can use this and you'll get fairly close. But if you do have the material properties for your dielectric fluid, you can create your own fluid data file to use within the tool. Just enter the fluid editor and then enter all of the data you have on your fluid. Hit save, and you can then use this custom fluid anywhere within the SSP software tool. With fluid properties ready, the next step is to design a heat exchanger. Go to the calculation menu to get started, select single phase, and then open a design template to get started. The default template is set up with both fluids being plain water, so the first step is to select the right fluids for our design. SWEP recommends to have fluid 1 be the hot fluid, so we'll change this to our custom ASIC dielectric cooling fluid we created earlier, and fluid 2 will be the 50-50 glycol water mix. Make sure the flow type is set to counter current and the exchanger selector set to B types. The next step is to set all of the units to match the earlier calculations done outside the tool. Now, I will be using US units and Fahrenheit. I know that's annoying, but that's the units of my pump curve charts and my system thermometers. Now, when entering power, temperatures, and flow rate values into the tool, the software can be a little difficult to work with. If you enter values that conflict or aren't physically possible with any of the heat exchangers in SWEP's libraries, the software will just give you a really vague error and not much else. And this is why those early hand calculations are important. They get you close enough for the tool to work. Now, when entering the values, it's important to lock down the numbers we really can't change. This would be the power or heat generated by the miners, the maximum temperature of the fluid coming off the miners and going into the heat exchanger, and the dielectric fluid flow through the miner tank. On the other side of the heat exchanger, using our hand calculations, maybe the maximum temperature coming off your dry cooler on a hot day is 108 degrees, and the pump flow rate is around 6.9 gallons per minute. Now, this is about all you can enter. You need to leave at least one box open on both sides of the calculator so the tool doesn't become over-constrained and give you an error. Hit the Calculate button and the tool will start selecting your heat exchangers. When the tool runs successfully, it will give you a ton of really useful data. It will suggest several heat exchanger options, including using multiple heat exchangers in parallel. It rates these options so you know which is best, and for each option, it gives you all of the operational parameters. And if you look at these numbers, they are fairly close to the numbers we hand calculated, which is really nice to see. If they are way off, it's a good sign you might want to check your math or how you entered the data into the SSP tool. Now from here, you can go to the SWEP website and look at more information on your selected heat exchanger model, or you can directly download the heat exchanger model data sheet. You can also click the dimensional tab at the bottom of the window. This will bring up a simple diagram of the heat exchanger size, and this is super valuable if you want to buy a heat exchanger from a different vendor. Look for a heat exchanger about the same size and width and having around the same number of plates. As always, it doesn't hurt to slightly oversize your heat exchanger, so if you can't find a model exactly the same size, go with one size bigger. From here, you can also do a lot of other calculations. You can lock down your heat exchanger model and then explore the different power ranges and cooling temperatures to see how the heat exchanger will perform. There's a multi-calculation tool you can use to automate this type of analysis. Like I said, it's a fairly powerful tool and super useful to help you design your home Bitcoin immersion mining setup. Hopefully this was a useful introduction to sizing heat exchangers. And if you're looking for more information on building a complete home mining setup or how you can design a system to work year-round, click here.